Hi, my name is Cristiana Larach, and today I'll be presenting my Lab 5 Choose Your Own Adventure. Introduction. So for this lab, I will analyze and model the motion of a volleyball being served. I was curious after doing the second lab for this class, in which we modeled drag, about how drag affects a volleyball being served since I played volleyball all through high school. The fundamental principles we'll be using for this lab is Newton's second law. The two forces we will be considering that are acting on the object are the weight force and the drag force, which we will model in two ways, turbulent drag force or normal drag force. So how will I do this? I will first use Tracker to track the motion of the ball, and then construct two computer models on GlowScript, one with turbulent drag and another with normal drag, and compare them to see which one models the motion best. Again, we're going to use Newton's second law, which is F equals ma, and this is part of the code that we will implement, which is that the final velocity is equal to the initial velocity plus the net force acting on the object divided by the mass of the object times delta t. Also, we're going to use that.
So first, I analyzed the motion of the volleyball using Tracker and tracking the center of mass throughout its entire motion, which lasted a total of 0.938 seconds, a little less than a whole second. I had to change the total frames per second since I took the video in slow motion, so the frames per second were 240. Then I used Tracker to calculate the initial velocity. I subtracted the x and y positions of two different time steps and then divided by the total time that passed, which gave me a vector of 3 meters per second in the positive x direction and 1.48 meters per second in the positive y direction. My system was the volleyball and the surroundings were both me and the earth.
This is the code for the turbulent drag. We first put the initial conditions, which was that the mass of the ball is 0.354 kilograms. Then we put that the position of the ball is this, which was almost 0. And the velocity of the ball is, like I said, the one we calculated in Tracker. The loop started at 0 seconds, and then delta t was a very small time step. We defined the gravitational constant 9.8, the unit vector for the positive y-axis, and the proportionality constant for the magnitude of the drag force. Then for our loop, we put the weight force, which is the mass of the ball, times the gravitational constant, times our unit vector in the positive y-hat direction. Then we put the force of turbulent drag, which we discussed before. And then we said that the net force is equal to the sum of these two forces. Then we use the Newton's second law to update the velocity of the object and the position of the object for each time step. Now for the code for our normal drag model, we had the same initial conditions, same everything. The only thing that changed was the force of drag, which is now negative b, the proportionality constant, times the velocity of the ball. Now let's take a look at what both of these models created on GlowScript. For the model for normal drag, these were the results. Turbulent drag, these were the results. You can't really see a difference between them here, but we will in a second.
These are my results. I plotted both the x position and y position of the observed data we got from Tracker and the data we got from both computer models of normal drag and turbulent drag. We can see that both computer models of drag severely underestimated the x and y positions. However, for the x position, the predicted position with the normal drag model did a better job at predicting the actual x position since it was slightly larger than the predicted position from the turbulent drag model. However, when we look at the y position, it's the opposite. The predicted position from the turbulent drag was actually more accurate than the predicted position from the normal drag since it was slightly higher. Now let's see, which model was the most accurate? Well, as we saw, for the x position, the model with normal drag was the most accurate. However, for the y position, the model with turbulent drag worked best. I wondered, why didn't I account for the contact force of my hand? Well, it was accounted for by the initial velocity determined by tracker, since I began analyzing the motion after my hand made contact with the ball, so there was no need to account for a contact force. Some improvements that could have been made to the lab is I could have recalculated the proportionality constant for the drag force, since I think that I used a very large one, and that's why the X and Y positions were so underestimated for the predicted model. Also, there could have been human error in tracker as I tracked the center of mass, and the camera angle could have also been improved. Thank you.